Okay, good morning, everyone. So we're working on getting the last few lectures done here. I made a small change to the autograder today that updates the judges. So when you have feedback for parts A, B, and C, it'll give you a little bit more meaningful feedback on if you got the test case wrong and it couldn't read what it expected to read, it'll give you better feedback on what it was that was invalid. Like it'll tell you like, oh, I couldn't find the decimal point in the middle of the cost on the first line, or I read an invalid character when I was trying to read the very first part of the cost before the decimal point. So make sure you start getting submissions in for Project 4. There's multiple parts of it. It's meant to be built in pieces and do parts A, B, C in that order. Also look at the Lab 10 autograder. The autograder for Lab 10 has a way for you to return a value and it will give you feedback on the autograder, and that does use a submission. So I would suggest reading over the problem and maybe submitting it with that value soon so that you can have that feedback on the autograder and you can go just click on the timestamp anytime you want to look at it. But try to solve the problem without reading what it gives you. Do as much as you can before you go to that help, but don't wait until the day it's due to get the help because it does use a submission. So today we're going to look at the knapsack problem and many ways to solve it, and we're going to look at shortest path. So the knapsack problem is a classical statement of this problem. It is not the most morally defensible statement of a problem, but this is the classic formulation. So the idea is you're a thief, and you find a safe that you're going to rob, and you find a bunch of items, and being a fairly good thief, you're good at estimating the size or the weight of an item, whatever's going to prevent you from taking it because it's too large or too heavy, and you're also very good at estimating the value of items. You have a knapsack which you fill with the items that you're going to steal, and if it doesn't fit in the knapsack or it's too heavy to fit in the knapsack, whatever measure we're using, then you can't take it. It's kind of hard to climb down the side of a building when you've got a painting in your arms that you cannot hold on to. So if it doesn't fit in the knapsack, you can't take it. So the knapsack has a certain capacity. And the capacity, we could state it in terms of size, we could state it in terms of weight. The exact word doesn't matter. It's like when we did our graph problems and MST. Does it represent the cost of laying the fiber optic cable, the miles of cable? It doesn't matter. It's our limiting factor. So we have every item has some sort of limiting factor on taking it or not taking it, and we have a knapsack which has a capacity on that feature. So the problem is you want to find the highest value that fits in the knapsack without exceeding the capacity. So if we look at just a simple example here, and I sorted all the items in increasing order of value and just happen to be increasing order by weight also. So we've got a capacity of, say, m equals 11, and we've got all these different items with various sizes and values, and we want to return the maximum value. Now, a slightly harder problem would be, don't just tell me the maximum value, tell me which items to pick also. Now, in code that we're able to fit on one slide, we had to return just the value. We didn't take the time to add the lines of code to decide which items were going to be taken and not taken. Now, there's variations on this knapsack problem. So the classic problem is known as the 0-1 knapsack problem, in which case every item that we find in the safe is unique, and we must either take an item or we leave it behind. Now, another possibility is a finite number of each item. Now we can, if we remove the fact that the items are unique, we could allow duplicate items. We could say, oh, there's an item of size value 6, size 2. There's another item of size 6, value 2. We just remove the unique restriction, and we can have a list with the duplicates explicitly stated. That's what I meant by explicit list here, is we'll explicitly list the items that have duplicates. Now, so that's one variation. Another variation is that we could assume there are infinite copies of each item. Well, really, no, they're not infinite, but there's more copies of each item than will fit in our knapsack. So that makes the problem a little bit easier, because then when we take an item, remember when we did the n queens problem, we had to say, oh, if I put a queen here, then it invalidates other choices, and we have to do that bookkeeping of, did we put a queen here or not, and how did we affect it? And then when we unchoose that queen, we have to make those locations available. Assuming infinite numbers of copies of each item makes the problem easier to solve, because we've got less bookkeeping to do. It's still going to be a pretty hard problem to solve, but we've got less code to do it. Another variation would be a fractional amount of each item. So with a fractional amount of each item, we could assume that there's items that have a very, very large number of copies, all with a very small value. For instance, if we had, I open the safe and I find a bag of gold dust. Well, I don't have to take the whole bag. I could use that gold dust to fill in the corners between other items. If I found a bag of very tiny diamonds, each diamond isn't worth a lot of money, but collectively they're worth a lot. And I could pour 3/4 of that in to fill in the corners between my other items. So when we don't have the fractional, we can't take fractions of an item. I either take the glass sculpture of a dragon, or I don't take it. Breaking the glass sculpture into pieces makes it useless. So the fractional knapsack is another variation on this theme. And like I said, we could use weight instead of size. Whatever we talk about for the limiting factor doesn't matter. Okay, so when we want to solve the knapsack problem, what could we do? Well, we could try brute force. We could try every combination of items, and we know we'll get the optimal solution. We could try a greedy approach. We could try dynamic programming. Backtracking, well, wait a minute. We're trying to maximize the value. So backtracking wouldn't help, because that's a constraint satisfaction. Backtracking would help decide whether we can take an item or not. But if we really want to take the highest value of items, branch and bound would work. So backtracking is not going to provide the type of solution we want, since we want to maximize value. So we've got 4 choices left that we can talk about. So one of them is the brute force approach. So there's n items in the safe. I start considering all possible subsets. There are 2 to the n of them, and I filter out the ones that will fit in the knapsack, and I'm going to discard anything with a size that's too big. And of the feasible ones, really, I don't need the whole feasible set. What I really need is the best I've seen so far and the one I'm working on right now. And this is also true in Project 4 Part C. We don't have to keep track of every solution we've found that gives us a cycle. We only need the best we've ever found and the one we're currently working on. And when we reach the level of a solution, then if the one that we're working on is better than the best so far, we update the best so far. Okay, so that's the brute force approach. The problem with the brute force approach is that taking or not taking every item means there are 2 to the nth things to consider. So the brute force pseudocode here says, hey, I'm going to run through every integer 1 to 2 to the n, and I'm going to generate the next item in the power set, which is a set of choices, and then I'm going to find the size of that possible set, I'm going to find the value of that possible set. And then if it's better than the best so far, I update the best so far. So this one, we actually do have the best set when we're done. We didn't return it, but we could say, hey, this is pseudocode. I can return max value, comma, best set. It's pseudocode. I don't have to worry about how to return two things at a time. Now, when we look at better ways of solving this, some of them are going to have actual code. So it'll be less easy to keep track of the best set. So there's our pseudocode for solving this. The problem with the brute force approach is that, like I said, there are 2 to the n possible ways to take or not take each of n items. And then checking the number of items picked by that set and summing up the values of those items and summing up the sizes takes n time, which gives us O of n times 2 to the n. And if there's more than like 4 or 5 items in there, if there's 20 or 30 items, while we're busy working through the 1 billion possible subsets of 30 items, what happens? The police show up. So this is not a good solution to the problem. We know it will give us an optimal answer, but we can't really afford the time it takes to do it this way. All right, let's look at a greedy approach. Now, the greedy approach seems like, well, at least it fits in with our whole robbing a safe sort of theme. So that's good. The problem first is, how do we be greedy about this particular problem? Do I be greedy in terms of highest value? Well, then if the large items have a high value, the reason it might not work is I might fill my knapsack with the 2 largest items because they had high value and then not be able to take anything else. And I might have unfilled space in my knapsack, and that's not good. What if I steal the lowest weight first, or the smallest size, or whatever? If I steal those, well, if they have a low value, I might fill up my knapsack with a bunch of low value items. So how can we be greedy about this? Well, let's look at, I should have added an extra copy of this slide in here. So we're on slide 9. I'm going to go back a ways. So here's our initial data. Let's get rid of that extra item. So if we say, let's try going with smallest items first. So let's do this up in the corner. So if I say, let's pick the smallest items first. So then I'm going to keep track of a column for the size and a column for the value. So we've got a capacity of 11. So I pick the first item. So I've got my capacity of 1 and a value of 1. All right. So I take the next item. It's got a value of 6 and a size of 2. Okay, I still haven't filled the knapsack. I can take the next item, fits. So a size of 5 and a value of 18. And now I've used up 7, 8. I've used up 8 of my 11 capacity. No other items fit, and my value, sum these up, is 25. Oops, that's a terrible 5. Okay, 25 is my value. All right, so what if we instead, let's just change colors. What if we go with the highest value? So that was the smallest size. If we go with highest value, and then I'm going to do this columns the same way. So we've got size and we've got the value. Okay, so if I go with the highest value first, I've got a value of 28 and a size of 7. That means I can't take that item. It doesn't fit in my remaining capacity. Can't take that item. I've got to take the item of value 6, which has a size of 2. So that's 9 out of the 11. So I picked this one, picked that one. I still have enough capacity to pick that one, so 1 and 1, and that gives me a value of 35. Well, that's better. So I've improved. So my first approach to small greedy got me a solution. My largest value got me a better value solution. Is there a different solution that gives us a higher value? How about the two that we just didn't pick that time. Those two fill up the capacity exactly. So I take the, if I take the size, and the value. So if I take the 518 and the 622, I get a value of 40, which happens to be the optimal for this one. So those two greedy approaches, neither one of them got me the optimal solution. What about if we, okay, let's go back to where we were. What about a different way of being greedy? So we said before that taking the highest value might cause problems, the small size might cause problems. What if we use both numbers? What if we figure out the ratio of the items and pick the highest ratio first? And that way we're not ignoring half of the data. So let's look at an example here. So this is a copy of that table with the ratios filled in. So now if we go with the highest ratio, I've got a size, and I've got a value, and so we go from the highest ratio. Well, it turns out that the highest ratio is in the same order as the highest value. So if we take the highest ratio first, well, we can keep track of the ratio also. So I take the ratio 4 item, it has a size of 7, a value of 28. I take the ratio 3.67 item, it's got a size, oh wait, nope, I can't take that one, it doesn't fit. Size of 6 doesn't fit in there. Okay, so I'd like to take that item, but I can't. So I took that one, can't take that one, can't take that one. The ratio 3 item, which has a size of 2 and a value of 6. The ratio 1 item, which has a size of 1 and a value of 1, I get 35, which we know is still not optimal. So we used more data, but we still didn't get the optimal solution. So this set of data was specifically designed to make sure that none of these greedy approaches work. So with some different data set, any one of these approaches might work. I think it might be hard to design a data set that all three would be optimal, but it would certainly be easy to say, hey, I'm going to design a data set for which this one works, or a data set for which that one works. So we're now running into a greedy solution that doesn't always work. It's kind of like making change. Making change with the US coin system always works no matter the amount. But if we change the coin system, some amounts work, some amounts don't. So same thing here. With certain values and sizes of items, this greedy approach might work or that one might work. So greedy is not always going to give us an optimal solution. So we can't use greedy. So we've got the pseudocode for it, and here I provided the, hey, let's build my table of ratios and let's sort by the ratios. And we're going to look at the complexity of this. So we know it's not going to be optimal, but we should at least finish the problem and analyze the complexity. So we go through and we sort the ratios. Well, we know that's going to be O of n log n to do the sorting. Building the ratios is O of n. So I sort them all by that, and then all I have to do is go through the items. If the item fits, I add its current size, I add its maximum value, and this whole loop here takes O of n time. So our greedy approach is nice in that it's n log n time to do the sorting, and that's the biggest complexity of the whole process. So it's n log n, and basically, even if we didn't do the greedy ratio, if we did any of the others, we might have to sort by size or sort by value. Whatever we have to sort by is the longest step, O of n log n. So not a terrible complexity. It's certainly way better than our brute force approach. And we might say, hey, if this is the best I can come up with, I might be willing to take the greedy approach if it keeps me from being there when the police arrive. Now, we've got to consider another variation. Now, the solution that we gave works for the unique, the 0, 1. It works for duplicate copies. It works for, it doesn't really work for infinite copies because we can't sort infinite things. But what about the fractional knapsack? What about if we choose fractional and we decide to be greedy? Well, then what happens? Let's go back to the slide that we had the data for everything. And what if we decided to use a fractional approach to this? Or, sorry, if we were told that fractional was allowed for this. So if we were told that fractional is allowed for this and we apply it, how could we be greedy? So think about this for a minute. Okay, that gave me time to get a drink of water. So now, I'm probably going to be talking while people start coming up with answers. What way would we want to be greedy if we were allowed, if we said we're allowed to do fractional? So if we're allowed to be fractional, is there any better way to get the highest value per amount of size than picking the highest ratio? So I pick the highest ratio and I get, okay, so now if I pick the highest ratio, so we're going to do fractional, highest ratio, and I take, let's write down how much size, and we take and how much value we get for it. Okay, so I take the item of size 7 and I get a value of 28. Now, that tells me if I started out with 11, I'm now down to 4 capacity remaining. That next item, I can't take all of it, but I can take 2/3 of it. So if I take 2/3 of that item, it takes 4 space, and I get a value of 2/3 times 22. Okay, so 2/3 times 22 would be 44 divided by 3, which is 14 and 2/3. Okay, so then I'm full. I can't take anything else. So what's my value? So now my total value is 28 plus 14 and 2/3 is 42 and 2/3, which is higher than we got when we did the optimal 0, 1 solution. Our optimal 0, 1 solution was take those two and get a value of 40 was the best we could do. And now with fractional greedy based on ratio, we got a higher value. So yes, it doesn't work with things like chopping up the Mona Lisa, but it does work with, let's say I open up the safe, and what do I find in it? I find a bag of tiny diamonds, I find a bag of gold dust, I find a bag of 128 gigabyte SD chips. Not even the cards, not even that big plastic case. I've got a bunch of 128 gigabyte SD chips. Which one of those has the highest value per weight? Turns out it's not the gold. Diamonds, it would depend on the size because they get their value goes up faster the larger they are. But certainly compared to gold dust, the 128 gigabyte SD chips, better weight per better value per weight ratio than gold. So if they're and I can't break those, but they are so small, the chips themselves are so small, I could take 50 of them, I could take 55 of them, I could take a fraction of what's there. So if we can take a fraction of an item, then fractional greedy does work. So it's good at least to see that with our whole thiefly theme, greedy works at least one time. So if we're allowed to be fractional, it does work. So next thing we can try is dynamic programming. So since we know that brute force takes too long and greedy might not give an optimal solution, since we want to take the whole piece of the item instead of breaking it up, we're going to try DP. So we're going to start out with a simple recursive version, and then once we've looked at the simple recursive version, we should be able to turn the recursive version that's not DP into a top-down DP. And we're also going to look at a bottom-up DP. Now, to keep these in a one slide per version format, we had to do two things. We had to just return the maximum value, and we had to assume an infinite number of each item because we don't keep track of what we've taken and have it taken. So that would, if we did both of those things, it would about triple the size of the code. So let's look at the recursive approach. So our basic recursive approach is for every item, if it fits, assuming it fits, I'm going to put it in my knapsack. And then what I'm going to do is I'm going to say, hey, I've got to make a recursive call with a smaller size knapsack. So if I started out with 11 and I take an item of size 4, I'd say, okay, let's make a recursive call for a knapsack of size 7. And every time I do this, I'm going to find the best packing for a knapsack of size 7, and then I return that to the upper level, which then gets to make a different choice. Then I can say, well, okay, well, what if I had 11 and I took an item of size 3, then I've got a capacity of 8. Let's make a recursive call to size 8. And maybe while I'm doing size 8, I say, well, let's take away an item of size 1, which leaves me size 7. Let's solve that again. So the directly recursive solution is going to be exponential because every time I take an item, I've got to solve a smaller problem. And if I don't remember the best way to solve 7, I have to resolve it all over again. So let's look at the approach for this, and this is actual code for this. So it says a knapsack problem. I've got a capacity, I'm given a array of items, and I've told how many items are in there. Okay, so I've got my space, so I've got a couple variables here. I've got my space, my maximum known. So max here is my best value for cap, for whatever capacity this is. So in this function, I'm going to figure out what's the best value for the given capacity. All right, so I've got a for loop. For loop says for every one of those n items, and notice this is zero-based, it's real code. So for every one of those n items, the space, think of this as the space remaining. If we pick item I. So this is the space remaining if we pick item I. If that space remaining is greater than or equal to 0, meaning if we didn't overfill the knapsack. So if we didn't overfill the knapsack, then we say, hey, what would be the value, v is just a temporary variable here, what would be the value of calling the recursive function on that smaller space plus the value of this item I? So we say make the recursive call on that smaller knapsack. Whatever it tells you the best value you can get is, add the value of this item, and then check if we've improved. If it's better than the best we've seen so far, we've got a new best maximum value seen for this size knapsack, and then we return that maximum when we're done. So we've got a recursive call. Let's look at how we get the complexity out of this. So we can go n times within the loop. So every time I'm going through this loop, I've got n choices I need to make, and I have to go recursively. So how many times can I go recursively? What's my maximum stack size? My maximum stack size is O of m, my initial capacity. Assuming we don't have any items of size 0. That's we should have said that up front. No items have a size of 0. So if I never have any items of size 0, I can never make more than m recursive calls. And every time I make a recursive call, I have to consider n things. So that's exponential. We're talking, well, okay, so it's either O of m to the n, or it's O of n to the m. Ooh, wait a minute. Which one of those is it? Well, think about, let's do a small one. What if I had 10 items and I only had a capacity of 2? Then I would have to go through like 10 items once, 10 items again. I'd have to go through 100 possible choices. I wouldn't have to go through 1,000 possible choices. So looks like we got the right one. So here. So it's O of n to the mth power. I've got to do n things, and then for each of those n things, I do recursion. For each of those, I do n things, I do a recursion, etc. So this is O of n to the m. It's exponential, but it's guaranteed to find me the best solution. Is it better than brute force? Well, wait a minute. Brute force was just 2 to the n. But remember, this one is going to do pruning. Anytime I would take an item that would overfill my knapsack, I don't take it. So I don't say, ooh, let's go to a capacity of -5 and try grabbing another item. So we don't do that. So it is going to do some pruning and keep us from making invalid choices followed by invalid choices. But it is going to take a long time to do. However, we can build some DP into this fairly easily. So here's our dynamic programming solution. Now, we've got this max known. And this is where it comes in a little bit of pseudocode, because max known is never declared anywhere. So what is max known? Max known, we could think of it as a member variable. Maybe knapsack top down, naptd, maybe this is a member function and the max known is a member variable. Now, if max known is a member variable, that's great, except then I could make the items, I could make n, I could make those member variables also and cut down on my parameters. And only the capacity would have to be, hey, let's call this with a smaller space. Let's call this with a smaller space. So max known is our memo. We got to figure out how big is our memo and what does it represent? What does everything in it mean? So notice that we do max known square brackets capacity. So max known has to be an array or a vector of size m plus 1. M plus 1 because we want to be able to have capacities in the range 0 up to m inclusive on both ends. So I want to allow that subscript to 0 just to make things easy for 1. And if I ever had to look up, like, what's the best value of a capacity of 0? What if let's say, I picked an item whose size exactly filled the knapsack? I would have to say, hey, let's make a recursive call on size 0. And I might do a square brackets there. So I want to make sure that that would work. So we're gonna make our max known vector of size m plus 1, And initially, it's going to be filled with all zeros. I don't know the maximum capacity for anything. So we get in here, we get into a recursive call at line 2, we check, hey, is the value greater than 0? Because if the value is greater than 0, I know it. I never recalculate anything twice. So once I know the best value for that capacity, it's in there. So if the value in there is greater than 0, it is known, I return it. Or if someone asks me for a capacity of 0, the value is there is going to be 0. And so I just return that 0. I say, hey, the best value of a knapsack of size 0 is 0. There's our base case. We have a base case when we hit a size of 0, a capacity of 0, and we hit a base case if we ever know something, the best way to do it. So we return that. The rest of the code is all the same. All of this is the same as the previous slide. The only difference really is in lines 2 and 3 and line 12 are the only changes to this code to make it top-down dynamic programming. Remember that Professor Darden said last time that often doing the top-down recursive is just a matter of taking the recursive and adding a little bit of code at the beginning to look for a value if we know it, and adding a little bit of code at the end to remember a value. So that's the changes we had to make for this to work. Now, before we look at how it works and go run through part of an example, let's look at the complexity, which is fairly easy to do. So here, we've got a loop that's going to run n times. So for any capacity, I'm going to have to run n times. But I'm never going to calculate a capacity more than once. Once I calculate the best way to do a given capacity, I store it in the array and a vector, and I never recalculate it. So I've got to figure out every capacity exactly once, and I have to run through every item and say, well, okay, for this capacity, could I take this item? So that's O of m times n. We never recalculate capacity, so we never go O over m, and we never look at an item twice for a given capacity, so we never go over n there. Now this is big O, it's not really big theta, because, for example, what if all the items were even? If all the items sizes were even, I wouldn't really be doing O of m, I'd be doing O of m over 2. But O of m over 2 is O of m. If all the items had the same size, there's a better one. If all the items were the same size, I would only have to hit a few of the capacities. You know, if every item was size 3 and just had different values, I'd have to go through, okay, capacity of 11, capacity of 8, capacity of 5, capacity of 2, and I'm done. So I would only run through a fraction of the capacities. So if all the capacities are multiples of a certain value, I won't hit all of the m, but I'll hit a portion of them. It's still O of m times n. Okay, so we're going to need some data here to be able to run through an example of this. I'm going to get just a second. I should have written those down. I'm going to pull up the slides real quick so I can get the values. Okay, so I'm going to erase what I've added to this slide so far, and we're going to add up at the top. We'll add the values and the sizes. And if you're at home, you can just open this up in another window. So we've got 1, 1, 6, 2, 18, 5, 22, 6, and 28, 7. Okay, so there is our sizes and values, and we want to run through part of an example of this. We're not going to run through the whole thing, because if I do a capacity of 11, then I'd have to do 11 times 5 items. I have to run through all 55 entries. And I don't want to take quite that long for this example, but let's start out at the beginning. So I call this with capacity of 11, and I say, okay, do I know the best value for a capacity of 11? No, because I don't know anything. All right. Actually, let's go smaller. Let's go somewhere we can get down to some cases a little bit quicker. Let's do m equals 5. So the very first time we call this, we've got a capacity of 5, and we say, do I know the best way to pack a knapsack of size 5? No, but let's go through things. All right, so I've got a space. So I've got my values, space. I've got cap, so cap is 5. Space I don't know. Max is 0. And V, I don't know yet. Okay, so now I've got to run through all the items. So for all the items, figure out the space remaining if I take this item. All right, so the first item has a size of 1. That would mean my space remaining is 4. Is my space greater than or equal to 0? Yes. So I've got to make a recursive call. I should have drawn these things out a little bit more where I had a little bit more room. Cap space and max. Okay, I'm just going to rewrite those. So I've got my capacity is 5, space is 4, max is 0, and V I don't know. All right, so I've got to make a recursive call in line 8 though. I've got to make a recursive call. Let's change colors. In my recursive call, I've got a capacity of 4. Do I know the best way to pack a knapsack size 4? No. So let's go run through the items. My space remaining in the recursive call, let's pick that first item. Remember, there's infinite copies because we didn't say, that first item's picked, or check if it's picked or unpick it or anything like that. I can say, okay, I can pick that first item. That means my space remaining is now 3 in the recursive call. And is that greater than or equal to 0? Yes, let's make a recursive call. Okay, change colors again. Knapsack of size 3. Do I know the best packing? No. All right, then, well, let's run through the items. First item, size 1, gives me space remaining of 2. Greater than or equal to 0? Yes. Oh, well, let's make a recursive call. Got to change colors again. Let's make a recursive call. Knapsack of size 2. Space remaining, do I know the best value for 2? No. Let's pick the first item. Size 1 remaining. Recursive call again. Capacity of size 1. Let's take that first item. Space remaining is 0. Is that greater than or equal to 0? Yes, it is. Let's make a recursive call. I make a recursive call down here to size 0. I'm getting really small down at the bottom there. Make a recursive call of size 0. Is the max known of 0 greater than 0? No. Is cap equal to 0? Yes, it is. I return 0. So back in the previous call, I got my colors right. So back in my recursive call here, I say, let's set V equal to the recursive call returned 0 plus this item's value is 1. So my V, I've finally gotten a V value of 1 right here. Is that greater than my max? Yes, it is. My max is now 1. Now, let's run through. Okay, we got to the bottom of the for loop. Let's go back through the for loop. Let's pick another item. Let's pick the item of size 2. So remember, right now my capacity is 1. Let's pick the item of size 2. That gives me a capacity of -1. Can't make a recursive call. Let's take the next item. Next item is size 5. That gives me a -4. Nope, can't make a recursive call. That's not greater than or equal to 0. Okay, how about picking the next item? Gives me a capacity or a space of -5. That's not valid, can't do that. Let's try the other one, -6. Okay, can't do that. I'm done with the for loop. There we go. And now I know one of my maxes. The max known for a capacity of 1 is 1. So, okay, hey, max known has 0 because size 0, the best is 0. And now at index 1, we have a 1 and everybody else is 0. Now we're going to go a little bit further with this. So now recursion unrolls. We are now back here, which I think is black. Okay, so I'm in the black line here. I say I tried to pick the item of size 1 1, I made a recursive call, and it returned a v of 1. My max known now for a knapsack of size 2 is 1. I've found a way to get a value of 1 out of a knapsack of size 2. Now we got to go through this for loop. See, remember, we're still in the middle of the for loop in this recursive call. So we go back and we try a different item. We say, okay, well, what if I picked item at index 1? That's the item of size 2. That would mean my space remaining would be 0. Is that greater than or equal to 0? Yes, so let's make a recursive call. I make a recursive call to size 0 again, and it returns 0. So, hey, my knapsack recursive call to size 0 returns 0, plus the value of this item is 6. Is this better than the best so far? Yes, it is. So now I've got a best value here of 6. And then more recursion happens. I will try things like I will try picking the item of size 1 followed by an item of size 1. I'd get a value of 2. 6 is better, etc. So we'll find the best for a capacity of size 2 is 6. The best for a capacity of size 3 would probably be 7, etc., etc. So that's our top-down dynamic programming. So let's go to the bottom-up. So bottom-up version says, this one, hey, max known is all in here. Everything's self-contained. Bottom-up, we're going to run some loops. So I've got my vector is created right here, size capacity plus 1 with all initialized to 0. I don't actually have to say comma 0, but I want to make it explicit. So we've filled the vector with size zeros, and we say, okay, let's start with a capacity of 1, because I already know the very first 0 in there is right. A knapsack of size 0 has a value of 0. Let's start at a capacity of 1, so that's I here. I is my capacity I'm working on. Yes, I think I made a mistake there, Joe. I think I made a mistake in this one. I think I got through that wrong. I've got, when I did a 1, I've got to make the recursive call. So I'd make the recursive call to size 1, I'd get a value of 1, then I'd get a capacity of 2. So I'd get 2 in here temporarily, and then we'd change it to 6. We'd find the better one after that. Yeah, I got lost in my recursion and my loops, which is uncommon for me. Okay, so in this one, in the bottom up, we're going to say, hey, I've got to run through every capacity. I know I have to solve a knapsack of capacity 1 before I can solve capacity 2, before I can solve capacity 3. So I'm going to go from bottom up. Whenever I need to look in max known, it's going to work. So we've got the line 5 here is a little bit confusing. Line 5 says my max known for I is equal to max known of I minus 1. So what this is saying is it's giving us a starting point. Think about later on. Like, let's say I found max known, I'll show the indices. So at index 0, 1, 2, 3, 4, etc. So initially this is all zeros. Initially this is all zeros. And then I find a way to get a 1 here. When I move up to a knapsack of size 2, what I say is, hey, even if no items will fit, even if there's no items that will fit in here, I can at least take the value of the one below me. I've got to be able to get a value of at least 1 out of this, because a smaller knapsack had a value of 1. and then we'll try to improve upon that. But it gives us a value here that's greater than 0, because if nothing fits in this size, I don't want to have 0 here. If nothing fits in here, like let's say they were all, let's do a slightly different example. What if they were all even items? If they were all even items, I would say, okay, well, knapsack of size 0 is value 0, 1 is 0, 2, I find out that, let's say 2 has a value of 6. Then I get to 3. Well, I'd say, let's pick items, but I have to go down to a knapsack of size 1. I might get problems if I don't at least get a 6 in here. So I want to get a 6 in here before I try picking items so that I don't leave off any possibilities. So that's what line 5 is for, is initializing the best capacity so far, or the best value for this capacity is at least as big as the knapsack smaller than me. Then we've got our for loop. This loop is kind of similar. It says, hey, let's run through all the items. Let's figure out the space remaining. If that space remaining is greater than or equal to 0, and the value would be better than what's in the array, in the vector, then update what's in the vector. So we don't wait until the loop is over. We just look at every possible item, because I know if space is greater than or equal to 0, I know this is a value that is done. It's already the best there can be. So I look up the smaller value for the smaller knapsack, the best value for the smaller knapsack. I add the value of this item, and if that's better than max known of I know a new max known of I. So I update max known of I, and then I run through every one of the j items. I run through every one of the I capacities, and when I'm all done, I return the last thing in the knapsack. And I could also say, since it's a vector, I could say max known dot back here instead of max known subcap, either way. So I return the last value in that vector, and I've got the best there is. So look at these. We've given you the code. Remember, don't copy and paste from a PDF, but if you type this code in, it's not that long. We can create the array of items from the slides pretty easily, and you can run through it and see what happens. And yes, I'm sorry I made a mistake on the top-down one. I got a little confused in my recursion and my loop at the same time. Okay, so sorry, I thought I had one more slide there on dynamic programming. So the dynamic programming, the bottom-up complexity, m times n. Hey, I've got a loop here that has to run m times. Oops, that's terrible looking m. I've got a loop here that has to run m times. I've got a loop inside of it that has to run n times O of m times n complexity. Now this one will run through things that don't really need to be done, because like I said, if we've got all even items, really, if I have all even items and my knapsack size is even, I will never need to fill in the odd ones, but it'll do it anyway. If we did the top-down approach would skip the calculation of all the odd knapsacks, because it just couldn't happen. We'd say, okay, I start with a knapsack of size 10, I reduce it to size 8, I reduce it to size 4, I reduce that to size 2. I never hit an odd size. Whereas the bottom-up might do a little extra work because it figures out how to fill odd-sized knapsacks that would never really be an issue. So they are both O of m times n. The top-down might do a little less work, but remember the top-down has recursive calls. I would do the one that you see the most sense in, the one that if you were trying to solve a DP problem on the exam, I would go with the one that makes the most sense to you. If you can write the recursive one without DP, then it's usually pretty easy to retrofit the top-down DP on top of the recursive implementation. So if you can write the recursive, you can probably write the top-down. You might see it as a bottom-up, is what occurs to you, and you can do it there. So yeah, really, I guess we could say for this one, we could say big theta of m times n, because it really is. It's going to run through all of them. Some of them it will skip pretty quickly because the item doesn't fit, and it reduces the space to a negative, but it still has to look at the item. So yeah, I guess this one would be big theta rather than big O. Whereas the top-down was definitely a big O. Now, for any problem that we would give you on the exam, you can do it top-down, you can do it bottom-up. There's a very small subset of DP problems that are solvable with DP that only one method works. And it's things where, like, the base cases are just not obvious, where simple base cases are obvious, but the restrictions are not obvious. So anything that we would give you, though, you can do either one. The time and the space complexity are going to be basically the same. We're going to have O of m. If I had m recursive calls, that's O of m also. And so on anything we'd give you on the exam, you can write it either way. Now, the DP solution, sorry, I've changed the slide again a little bit too early. The DP solution is optimal. It will find the best solution. It does so much faster than the brute force approach, which was n to the m power. So it's much faster than the brute force. It's a little bit slower than the greedy, but it always finds an optimal solution. Now, another thing we could do is we could say, hey, what about backtracking and branch and bound? Well, we already said no to backtracking because that's just constraint satisfaction, but we could do branch and bound. Now, if I told you that the DP solution is optimal, when would I have to use branch and bound? There is a circumstance. There's something that we've been doing this whole time with our knapsack, which isn't really a restriction. And it's something that makes DP possible. Is if we look at our items, remember we had items with, and remove my marks here, remember we had a value and we had size. The values were like 1, 6, 22, 18, and 7, 8, I don't remember. Anyway, and size is like 1, 2, 5, 6, 7. Okay. What if something here wasn't an integer? What if these values were doubles? Well, if the values were doubles, then I would have to make this vector a vector of doubles, because that's the value. So for a given knapsack, maybe it's worth, I'm really good at estimating the value of items. That's not worth $22. That's worth $22.57. Mm-hmm. So if the values were doubles, we would have to change it to a vector of doubles. Not a big deal. But what happens if the sizes were doubles? Remember, I am subscripting by, so remember, I is a capacity, and I'm subscripting by I. What if the remaining capacity and the space remaining, that I have to say, hey, let's look up the space remaining. Hey, I started out with a knapsack of size 12, but now I picked an item of size 2.3427. And now my remaining capacity isn't an integer anymore. So now I can't use it as a subscript. You might say, hey, you could just use hash tables. I could, except for two problems that occur. One is that the math might produce round-off errors, and I might look up the best known value for a knapsack of 10.4372 and 4.7319999999, and they should be the same, but they're not. And so I've got a round-off error giving me a problem. So if the values are doubles, we can't do DP. Also remember the number of doubles. See, before I knew that the capacity was in the range 0 to m. I needed m plus 1 possible capacities. But now when I start subtracting doubles, I could pick this item and then that item and then a different item. The number of possible capacities goes exponential, and I don't have exponential space. So I have a round-off issue and I have an exponential space issue. So if the values associated with each item are not an integer, we can't do DP, but we can fall back on branch and bound. So when we fall back on branch and bound here, this is a good example of how things have to change. So when I start out, I need a best so far, my initial estimate. Now I could say my best so far is 0. I don't know anything. I don't know the best way to pack a knapsack. 0 is the best I know, but if I do that, I can't prune enough. I would like, it says here, I need an initial estimate. I need an initial estimate. It could be 0, but it would be much better if I had an initial estimate that was greater than 0. It has to be a lower bound, though. Why? Because if I tell you the best value for this knapsack, my best guess, my initial guess is 50. Well, if you can never improve upon that, because 50 isn't even possible, you're going to run into problems. So that's why the initial estimate must be a lower bound. So how can we get a lower bound? And I'm going to let you think about this. I'm going to talk about the upper bound, my estimate so far, and I'm going to come back and see if I've got some answers. So that's my initial estimate is going to be a lower bound. Then I'm going to need a way to estimate. So I've picked an item, I've got a remaining capacity, and I want to know, does it look good so far? Does picking that small item, or that low value item with a big size, does that look like a good way to begin? Well, to know that, I've got to have a way to get an estimate on the remaining. That estimate must be an upper bound. It must be greater than or equal to reality. If it's less than reality, if I say, well, you pick the item of, size 1 with a value of 10, but the estimate of remaining value is 0, you'd say, oh, well, I've got a way to get 11. That 10 plus 0 is not better than my 11 that I know. Let's not start that way. So if it's an underestimate, I might prune too much. So this one has to be greater than or equal to the actual cost of the remaining knapsack. So that's why it has to be an upper bound. And if this value is less than the best so far, I eliminate it. So everything here is sort of reversed from traveling salesperson. With traveling salesperson, because we are trying to minimize, we needed an upper bound initial estimate and we needed a lower bound remaining estimate. Here, since we're trying to maximize instead of minimize, everything has to reverse. So, how do I get an initial estimate that is less than or equal to reality, and how do I get an estimate of the remaining portion that's greater than or equal to reality? Now, these are things we've already talked about today. We can use something we've already talked about today to do these. So this is where greedy can come in. We could be greedy here. Hey, it's better than 0. It may not be the best. We could get lucky. Per a certain set of data, we could get lucky and our greedy would be optimal. And then we would be able to prune really quickly. We'd be able to prune lots. Okay, so that's our initial estimate, be greedy, and we'll talk in a minute about which way to be greedy. But then how do we get an upper bound? How do I get an estimate of the remaining capacity that might be greater than or equal to reality? How about if we do greedy, fractional, based on the ratio? And that means I've got to sort everything up front. So here I may as well do greedy ratio just because I'm going to sort them once. I'm going to sort them once by ratio, and I'm going to loop through them in ratio order. I may as well do both greedy approaches using the same one. I know this one is not guaranteed to be optimal. I don't care. I just want it to be done quickly. So if I do the sorting up front, then my estimator here is cost O of n. Not O of n to the mth power, just O of n. So this is a big improvement in speed. So if we have to do branch and bound because we've got doubles as our values, we could do a greedy, any greedy for the initial, and we'd do a greedy fractional ratio for our estimate of the remaining value. And since we're doing greedy fractional ratio, we may as well make our first greedy be ratio anyway, because we've got to sort it in some way in order to be greedy. Okay, so that's when we would fall back on branch and bound, is when DP can't be done because the capacities and the sizes of the items are doubles. Okay, so we looked at lots of different approaches. We saw why backtracking doesn't work. We saw why brute force is too slow. We saw that dynamic programming will always work if it's integer sizes, and greedy will sometimes work, sometimes won't. In some subproblems, like fractional, greedy is the best way to do it, even better than DP. So greedy fractional is faster even than DP. And then we saw when we'd have to fall back on branch and bound. Now we're going to talk about shortest path algorithms, and there are more slides here than we are going to go through today. So we're going to talk about what the basic idea is and how it comes up, and look at one way to solve it. So let's say we're talking about the highway system. We want to figure out how to get from, say, Ann Arbor to your, you've got an internship in normal times, not COVID times, which would be online, but you've got an internship that's in, say, New York, and you don't like to fly, so you decide to drive. That's fine. You probably want to minimize your total distance, or maybe minimize your travel time. If you're driving around town, maybe you want to minimize your number of stoplights. Maybe the people writing the software have been paid to maximize the number of Krispy Kremes you are forced to drive past and think about stopping. So there's lots of things that we could try to minimize or maximize. There's one in here that is actually used in routing schemes every day that's not in this list. And you may have heard about it. If we're talking about delivery vehicles, what's another thing that they try to minimize? They try to minimize left-hand turns. Why? Because they found that making left-hand turns costs money. And so companies like UPS and FedEx, they have software that minimizes left-hand turns in many situations. And so their software basically decides, like, is this intersection always okay to do a left-hand turn because it never has traffic? Do you have to base it on the traffic? Do you never ever make a left-hand turn there? And so their software will route them. They'll be like, the software will say, go through this intersection, make a right-hand turn, a right-hand turn, a right-hand turn, and go straight through that intersection is going to cost you less time than making a left-hand turn and waiting for the light. And they actually saved, when they implemented that, started saving on the order of $1 billion a year in gas money and time and salaries and overtime to get deliveries made and stuff like that. So sometimes that odd metric can be what you want to optimize. If we were looking at an airport system, like, hey, I've got to fly, I want to fly from here to my job in San Francisco, and I want to minimize my fare, or I want to minimize my travel time, I want to minimize my number of layovers. Now, if I want to minimize the number of layovers, then everything has an equal cost, and we don't need what we're doing today. We could use the breadth first search if we're just trying to minimize number of layovers, because every layover has an equal cost. But if we're trying to minimize our fare or minimize our travel time, we have to consider that, hey, maybe the 2 layovers is going to cost me $200 less than the 1 layover. So that's where we need the algorithm from today. So weighted path example. So what we're trying to do is we're trying to find a weighted path length that's minimal. So if I've got an edge weighted graph and I've got some function C that will give me the cost of the weight of the edge from VI to VJ, I want to produce a path. I want to have a non-empty sequence of vertices, vertex 1, 2, 3, etc. And I've got a function to give me the total cost. So if you give me the path, then I can take that path, I can give every pair of vertices in that path to my cost function and figure out the total weight. So the general problem that I'm trying to do is I'm trying to get the smallest total weight. So one thing that we're going to talk about is really when we ask navigation software for a route, we've got a specific starting point where I am now, and we've got a particular endpoint in mind where I want to go. And that would be a shortest path between 2 fixed vertices. Now we're going to find that as we do this, whatever we pick as our starting vertex, we're actually going to find what's called single source shortest path. Whatever vertex we start with, we're going to find the shortest path from there to everywhere. Because I don't know if I've got the shortest path from VS to my destination vertex unless I've gone to every vertex, because maybe the best way to get to my destination is to go through 3 other vertices. So along the way, trying to solve this problem, we're going to solve other problems also. So that's why it's called single source shortest path. Even though I have 2 endpoints in mind, I'm going to get more than one shortest path in there. Okay, so here's a graph, and here's the edges, and this one happens to be directed. It could be directed, it could be undirected. So I've got a directed graph here, and I'm trying to find a path from B to F. And there I've shown the shortest weighted path with the 3 and the 1, and so 3 and 1 and 4 and 1 is my shortest weighted path to get there. If I take anything else like 3, 1, 2, 5, 3, 1, 2, 5 would be longer than the 3, 1, 4, 1. Or if I start out going by the 5 to get to C, then 5 plus 4 plus 1 is longer than 3, 1 plus 4 plus 1. Now, if I just want the shortest unweighted path, the shortest unweighted path is what's shown here. I want 3 edges. All edges have equal cost. They're all an edge. I could do that with breadth first search. But for the shortest weighted path, I need what we're going to do today. Now, in general, the shortest path problem is undefined for graphs with negative cost cycles. So if I discovered that, hey, I would like to travel from here to San Francisco, but I found a route where if I fly from here to Chicago and then fly to Toledo and then fly back to Detroit, the leg from Chicago to Toledo, they hand me $800 for getting on the flight. and it only cost me $600 to fly from here to Chicago and Toledo to Detroit. You know what? This year my vacation is going to consist of lots of flights where people hand me money. And yeah, I never go anywhere else other than those 3 airports, and I get really, really tired of seeing them. But hey, for a couple days, making $200 every couple hours is a pretty good vacation for this year. Maybe next year I'll do something different. Probably by next year they won't pay people $800 to fly from Chicago to Toledo. They'll fix that problem. So in terms of real world problems, negative cost cycles is generally not an issue. So shortest path is undefined when there are negative cycles, because you find the best way to do it is to go through the cycle and get that money paid to you. Now, Dijkstra's algorithm is the algorithm that we're going to particularly look at for solving shortest path. Dijkstra assumes there are no negative weights whatsoever. So if there is a negative weight, Dijkstra will not necessarily give the right answer. Some case that might, some case that might not. It's not guaranteed to give the right answer. You cannot fix it. You cannot say, well, what if we modify it a little bit to do this instead of that? No, it doesn't work. Dijkstra's algorithm just doesn't work with negative weights. Even if the cost of the cycle is positive, Dijkstra might still give the wrong answer if there's a negative weight in there. And the reason why is that Dijkstra assumes once you know the best way to get to city X, you know it. With negative weights somewhere else, you might find, well, wait a minute, even though I know the best way there is to get to X, a negative weight might make me change my mind. And changing my mind is not allowed in a greedy algorithm. So for Dijkstra's greedy algorithm to work, there must be no negative weights whatsoever. Okay, so for Dijkstra's algorithm, we're going to keep track of some data about each vertex. We're going to have to remember, for every vertex, do we know the best path to that vertex, true or false? Initially, it's false for everything. What is the shortest path from VS to that vertex? Initially, it's infinity for everybody except the starting vertex is 0. And what is the predecessor vertex? Where were we before we got to vertex V? Initially, it's unknown for everybody. Sounds a lot like Prim's table. And in fact, Dijkstra's algorithm is much like Prim's algorithm with one change. So the data, the table is going to look exactly the same. How we calculate things is going to have one difference. So we've got here an example, and I want to find all the shortest paths to B. Really what I'm saying is, like, I started out with a question like, hey, what's the shortest path to go from B to F? That was my initial question. So I said, oh, well, B is your starting vertex. Let's start out making B 0. Now, really, I'm not going to find all the shortest paths to B. I'm going to find out all the shortest paths from B. But, let's say that I asked a different question up front. Let's say I asked the question, I would like to know I want to know the shortest path from F to B. If I choose B to be a distance of 0, I will get all the shortest paths to B. This only works because it's undirected. If it's a directed graph, we have to stick with the actual starting point. So if it was a directed graph, if B starts out at a distance of 0, I will find the shortest paths from B to everything else. So in a directed graph, our starting point matters and our directionality matters. So if I was saying, hey, I'd like to go from F to B, I would have to start in a directed graph. I would have to start out F is the one with a distance of 0 because F is my starting point. In an undirected graph, we can change it a little bit and change things around, and I'll show you why when we get done with this example. So starting out here, we said, hey, let's start b at a distance of 0. All right, so what we've got to do is it's going to be really similar to Prim's algorithm. I'll show you how it's different. So I'm going to have to know a current vertex and a current distance. Initially, my current distance is infinity, and I've got to find the smallest false one. So A is false, that's infinity, it's not better. B is false, its distance is 0, so that's better. So I get B at a distance of 0. C is false, but it's not better. D, E, F are all false, but not better. I've found my current vertex. That's step 1. Step 2 is I mark B as true. And step 3 is I update all of B's neighbors. Okay, so I can go from B to A at a cost of 3. So I can reach A at a cost of 3. 3 is better than infinity if I get there from B. B is already true. We can't, whoops, threw my pencil on the floor. And, oh no. I have a slight problem. I lost the cap to my Apple Pencil. I've got to find it before a cat does. Okay, sorry about that. I'll be more careful in the future. All right, so we've got to update things adjacent to B. So we've updated A. B is true, we can't change that. B to C. Hey, I can get to C at a cost of 5. That's better if I use B as a predecessor. D, I can't get there. E, F are all false, but I can't get there. So I've updated all the neighbors. So now I know all the paths. Let's just go with the actual way we should be doing this is I know all the paths from B to A and C. I've updated those. So I know the best way to get to B is to start there. A and C, I know some decent ways to get there, but I don't know that they're the best so far. Okay, so let's start. Again, we've got to find what is our smallest false one and what is our current distance. Okay, so we start out with infinity and we check A. Hey, A is false. It's a distance of 3. B is true, we can't look at it. C is false, 5's not better. D, E, F are all false, but they're not better. We found the smallest false one. All right, so we mark A as true. We mark A as true. So now we know the best way to get to A, and we've got to update A's neighbors. All right, so I've got to update A's neighbors. So let's run through the loop. A is already true, we can't change it. B is already true, we can't change it. We get to C. All right, C. Hey, I could get to C at a lower cost than 5, right? What is my cost to get from B to C? It's not 1. 1 would be what we did in an MST. Here we've got to consider the entire length of this path, which is our current distance plus the new edge. So hey, I know a better way to get from A to C. It's the current distance plus that edge would be 4. 4 is better than 5. So I put a 4 in here and I say, hey, you would get there not from B, you'd get there from A. All right, what about D? D is false. Can we get from A to D at a cost better than infinity? Yes, we can, because I've got a cost of 3 plus 5. 3 plus 5 is 8. 8 is better than infinity. I've found a better way to get to D, is to get there from A. Now, A to E is infinity. That's not better. And E is false. F is false. Don't have a better way to get there. So we've updated all the neighbors. There's where we are right now. So I've got to go back through. Current distance is infinity. Let's find the smallest false one. True 1, false 1. So C is false. It's a distance of 4 is better than infinity. D is false, but it's not better. E and F are false, but they're not better. So we found the smallest false one. We mark C as true. And then we update, and I can just do this here. I haven't been doing that. So C is now true. We've got to update the neighbors. So we go through the loop. A is already true, B is already true, C is already true. D, do I have a better way to get to D? Well, I could use a cost of 4 to get to C, plus 2 more is 6. Hey, that 6 is better than 8, so I could get to D at a cost of 6 if I get to D from C. What about E? E is false. I can get to E at a cost of 4 plus 4 is 8. That's better than infinity if I get there from C. What about F? F is false, but I can't get there from C at cost from C is infinity. 4 plus infinity is not better than infinity. And this is a place where the double numeric limits of double infinity is great, because I'd say, hey, let's look at this. Is 4 plus infinity less than infinity? No, it's not. We don't pick it. All right, so we've finished updating the neighbors of C. We go back through the outer loop. So I go through step 1. Let's find the smallest false one. True, true, true. 6 for D. 8 is not an improvement. Infinity is not an improvement. Okay, I found the smallest false one. I mark it as true. And then I've got to update the neighbors. Okay, so have I found a better way to get to E? Well, I've got a cost of 6 plus infinity from D to E. That doesn't help. That's not better. How about F? I've got 6 plus 5 is 11. That's better than infinity. So it's 11 if I get there from D. All right, I've updated all the false ones. Go back. We've got to find the smallest false one. So, true, 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 true. 8 if I go to E next. F is false, but it's not an improvement. So that's my next one. I mark E as true. And then I update the neighbors. True, 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 true. False. Aha, F is false. I can get to F at a cost of 8 plus 1 is better than 11. So I can get there at a cost of 9 if I get there from E. All right, so I updated everything. Now I go through. I found the smallest false one. Infinity, distance of 9 is better than that. Vertex F. We mark F as true. We update all the neighbors. There's no one to update because they're all true. And we're done. So that's what's in our table. And now what we know is, really, if this was a directed graph, we'd have to say it this way. I know the best way to get from vertex B to everywhere else. And really, though, oops, sorry, I'd labeled this in the wrong direction. So the reason I labeled it is, let's say there was no one-way streets. Let's say it was all undirected graph. Think about this. If I draw the arrows the way I drew them instead of the proper way, so really I'm going to draw them in purple, they really should be like this because we said B was our starting point. But if they were all undirected edges, I could say, hey, what I really want to do is I want to get to B. Let's make B a distance of 0. Why would I do this? Because my software, my navigation software, has found me all the best ways to get to B. When I start out at home, which is F, when I start out at home here, I go down to the end of my street and I see, oh, look at that. There's an accident to the west of me. I can't go that way because there's an accident down there. Let's go north. Let's go to D. So I get to D, my software, so now I follow this one instead. I get to D, and my software does not have to recalculate. It says, well, now that you're at D, I know the best way to get from everywhere to B. Let's go this way. So this is why we showed it this way, but really the arrows should be drawn the way they are in purple right there, is if we start by saying B is 0, really we've found B2 everywhere else. If it's undirected, it works either way. But if it's a directed graph, it really does matter which way you solve the problem. Now, in a real-world GPS system, there's a lot more to it than this, because when you say, find me the directions from, say, home to my favorite restaurant 10 miles away, the GPS system doesn't say, okay, well, I've got every intersection in the US. Let's do Dijkstra's algorithm for every intersection in the US. There's just too many of them. Even at an n squared, there'd be way too many. So what it has to do is restrict it. So it might say draw an ellipse around the start and the destination. You're not allowed to go outside of that ellipse because it would just be too big. It would just be too far out of the way. It's too much to consider. And then once we've drawn that ellipse, we might say, okay, well now we can't still do every intersection in that ellipse. Let's find the big routes first. Let's say, hey, they didn't say avoid highways, so let's use highways to get 90% of the distance done, and then we can solve the home to the highway, highway to the destination problem separately. Is a lot more reasonable problem. So sometimes a big navigation system with a long route it's going to have to break it into subproblems, because even just say going from Ypsilanti to Ann Arbor, there might be thousands and thousands of intersections to consider. You don't necessarily have time to do them all. Oops, let me draw with my finger. Okay, so Dijkstra's complexity. So Dijkstra's algorithm is O of V squared if we do a nested loop implementation, and it's a lot like Prim's. The only difference between Dijkstra and Prim is how you calculate the updated distance for a neighbor. In Prim's, it's always the cost of a new edge. In Dijkstra, it's the current distance. It's always current distance plus the cost of it. Oh, wait, let's go back one more. It's always current distance plus the cost of a new edge when we do Dijkstra's. That's the only real difference in the algorithm, and the complexity ends up being the same because it's just one calculation different. Dijkstra has an addition where Prim's does not. It's same complexity, just a slightly bigger constant for Dijkstra. If we do it with sparse graphs and we use binary heaps, we can get O of E log V by doing the priority queues, binary heaps. And we've got the complexity here, which we already ran through this for the Prim's algorithm. So we went through this whole thing with Prim's algorithm, and we filled in the complexities. The only real difference here is that's the different line from Prim's algorithm. Prim's algorithm said, hey, let's figure out what the weight would be and see if it's better. This one says, let's figure out what the sum would be and figure out if it's better. So the rest of this complexity is all the same. And then for when we're done, we've got to run through and build our set of directions, because I've got a table. I've got to list out my directions in a more readable format. Okay, so we're a bit over time here. There's an example here that you can run through. I'm going to skip past this for a minute and get to the last things we're going to do today. So if we wanted to do all pairs shortest path, so not just single source shortest path, but I wanted to do all pairs, one solution would be, hey, I've got Dijkstra. Let's just run Dijkstra V times and do it with a different starting point each time. Other ways to do it is we could use Floyd's or Floyd-Warshall's algorithm for a dense graph. There's another algorithm that works on sparse graphs for all pairs shortest path, which you don't even really have to even know the names of these. The Floyd-Warshall's algorithm is in the slides. We used to do it, and then we found that we just never had time to get through all of it. It was very, very rare that we got through all of it. And there's also better topics. So now that we've eliminated things like linked lists, because 280 does linked lists, we had time for new things. So we still eliminated Floyd Warshall because there's other cooler stuff to look at. But I hate deleting perfectly good slides, so they're in here. But we are not going to ask you anything beyond. Let's see, so this is Floyd's algorithm, blah blah. So you don't need to know that. You don't need to know this. I would say let's just stop right there. That's what you need to know. Is you could do that. We could take what we know with Dijkstra and we could run it with every vertex as the start vertex, and then we'd have all the pairs. Okay, and then this example, it says find the shortest path from O to T. So if we do it the way it should be, this means O has a distance equal to 0. Because it is our starting point, we set O's distance to 0, and it is possible to do this without the table. You've just got to be really, really careful. We say, okay, right now, everything that's not labeled in my markings, I don't know. Okay, I know this one has a distance of 0. It's true. And I update the neighbors. Okay, I can get to A at a cost of 2. I can do B at a cost of 5. I can get C at a cost of 4, but I don't know any of those. Now, let's find the smallest false one. Okay, smallest false one is A. So A is now true. And then let's update the neighbors. Okay, I can get to B at a cost of 4 instead of 5. I can get to F at a cost of, that's the 12 edge is still there. I can get to F at a cost of 14. I can get to D at a cost of 9. And so it is possible to do this without the table if you're really careful. And yes, so if we run Dijkstra V different times, we would need V tables to store all the information. So we'd have V different starting locations, we'd have V different tables to track our data that we need. But there is no question on this on the exam. Okay, so you can finish this example yourself as practice. And that's it for today. We'll see you in office hours if you need help on the project or the labs.